an exciting new topic about building expert systems using fuzzy logic. To understand fuzzy logic, we need to look at fuzzy set theory. And before that, let's link today's topic with the previous topics. We have learned till now how to handle uncertainty using confidence factors, probabilistic reasoning, and today we will do fuzzy logic. We also learned propositional logic and implemented an expert system using PyNo or Experta package. Today, I will introduce you to fuzzy set and fuzzy logic, linguistic variables, and universe of discourse are going to be two new keywords that you will learn. These linguistic variables will be expressed using a function, we will call it membership function. We will learn that fuzzy variables are similar to the normal variables that we work with in expert systems, data science, and other problems, but they can be operated on using special operators, fuzzy operators. At the end of this topic, we will also exercise these concepts in fuzzy logic-based expert system implemented in Python. So handling uncertainty using confidence factors, if you remember, we can have uncertainty in the information or in the reasoning and rule. In the way using confidence factors, we conclude that multiplying both the uncertainties give us the uncertainty in the conclusion or consequent. The second way was probabilistic Bayesian way. Probability of B given A we could calculate using Bayesian formula of P A given B and P of B divided by P of A. We called this probability of A given B as the likelihood, probability of B as the prior, and probability of A as the total evidence. Now, why do we need a new technique to handle uncertainty? I will explain with this example where we have three columns. The second column shows the temperature in Fahrenheit. The values are 32, 50, 70, and 90. Each value corresponds to the comfort level for that temperature indoors. For 32, it will be freezing temperature. Around 50, we will say it's cool. 70 will be warm enough, and 90 will be hot. If you want to represent these numbers using words freezing, cool, warm, and hot, we can say that when the temperature is 32, it's freezing, and the membership on y-axis for 32 value is 1, for 50 value is 1 for cool, for 70 value it's warm, for 90 it's hot. But the question is, will it be hot if the value is 89? If the temperature is 89, how much hot will it be? If 90 is perfectly hot on y-axis, 90 is the membership to the set of hot, value 90 is 1. Temperature 90 has value 1 for hot, then what will be 91 and 89 or 85? You would agree that 85 value will be slightly warmer but less than hot. How about 75? Will it be hot or warm? So the need arises that we need a representation where we can assign one number to multiple groups. One temperature can be hot and warm at the same time. Would you like to say something about that? Muhammad Ali? Ruithan?
It's near 50%.
Right. So Percentage is one way we can use percentage, but the idea is that instead of assigning one value to hot group and one value to warm group, there is a good case for assigning a temperature to multiple groups, multiple sets. One temperature can be slightly warm and slightly hot, right? So if we have that need, in that case, we can create this kind of rule instead of saying when let's say we want to create a rule to change the temperature of air conditioning, and we say when comfort level is cool, then turn heater high. Now we don't know what is cool. Cool is not a number. A number or temperature represented by number can be slightly cool at the same time slightly warm. In we don't know how to represent high. A number can be high at the same time medium. Between medium and high, all the numbers will be belonging to both high and medium. So there is a need that we can represent this kind of uncertainty or ambiguity in language. So comfort level, when it is cool, this is imprecise information. And turning heater high, how much high? We cannot represent high with a single number. So that kind of uncertainty we cannot handle with probabilistic or confidence factor techniques. So in human language and daily interactions with systems, we come across with vagueness in language. What we talk, it doesn't have a crisp meaning or numeric representation. Everybody has a subjective context associated with the words that we use. That's why natural language is ambiguous sometimes and like not distinctive, not certain. So most of the concepts that we deal with, human world, they have a degree of blurredness in these concepts. So since humans need to use machines, there should be a way that we can convey that vagueness to machine, a computational way. Fuzzy logic or fuzzy set is the answer to capture that vagueness. It's a knowledge representation way to represent and capture imprecise notions, events, and concepts. In this way of thinking, what we allow is that one number can be associated with multiple sets. In crisp sets, normal mathematical sets, one number belongs to only one set. Odd numbers, even numbers are two separate sets, mutually exclusive. But in case of fuzzy sets, one number will be associated maybe with more than one set, fuzzy sets, with a degree of membership. And degree of membership will be measured in the range of 0 to 1. So if we allow this facility, we can map qualitative with quantitative. We can use words to represent numbers. Fuzzy sets allow a number to be associated with multiple sets, and fuzzy logic is the way we use those fuzzy sets to compute something for us in an intelligent way to build expert systems that interact with machines using human natural language and capture that uncertainty that we have in language. We cannot say that fuzzy logic is a logic that is fuzzy. Instead, it's a logic that is used to handle fuzziness. Fuzzy logic reflects how we think. and it models our sense of words, and the it builds a bridge between human language and the the systems, cyber systems, computational systems. If you look closely, all the measures that we have in data, age, temperature, height, speed, miles per gallon, uh, brightness, all the variables that we deal with, price, they have a degree of uncertainty in the meaning. Age variable is, we want to define it in a way that it's meaningful to us. So we can say kid, teen, young, middle age, old age. So what numbers will you put? The boundary to define young will be a challenge, because we cannot say age 30 is young or middle age. It will be slightly middle age and slightly young age, right? So we take this concept of fuzzy set theory, which is linguistic variable. So instead of creating uh, the normal variables we use in computing, we create linguistic variables that represent numbers in terms of words that we use to talk about numbers. It's an efficient and resourceful way to solve some problems that we cannot solve with the normal crisp set theory or probabilistic way of thinking. For example, temperature controller. If you want to talk to your cooling machine or indoor air conditioning system, and you want to say, I'm feeling cold, please warm up the room a little. You won't like to say that I'm feeling cold, temperature 30, and please raise the temperature up to 72. That won't be a human way to talk to a machine. You would just say that I'm feeling cold, please warm up the room. So the expert system, or the machine should be able to understand what you are feeling and how to respond to that request. Other than temperature controllers, in the famous example of application of fuzzy logic is APS, anti-lock brake systems, use linguistic variables. Originated in 1965 by Professor Lotfi, the fuzzy logic has created a lot of interest and a separate school of thought in computing that strongly believes in this kind of constructs and the way of programming machines. We use linguistic variables where the values of those variables are words. And those words allow some imprecision, and that brings some exceptional interesting applications to fuzzy logic. So the better we can use those words, the better we can model the reality. This paradigm of programming and computing is also referred to as computing with word, or CWW methodology. So fuzzy set theory is well grounded in statistics and mathematics, because all the operators that we have for crisp set theory, we have corresponding operators and proofs and theorems for the fuzzy set. There are many interesting applications that you can find. A famous example is the train controlled by fuzzy controllers, fuzzy logic controllers built in Japan. The cameras, first Nikon camera company introduced cameras that use fuzzy logic to control the quality of photos that they take. This machine that is commonly used in East Asia to cook rice uses fuzzy logic. Air conditioning machines use fuzzy logic. So many other examples you can find. When you go shopping appliances, you can read fuzzy written on the manuals, fuzzy logic implementation. Let's see how it works. The example of crisp sets is here. We are looking at three lists: a list of fruits, a list of characters, or even numbers. And we can represent them using well-defined notation. So classical sets. In classical sets, one member is either the degree of membership for the elements of the set is either 0 or 1. So here, all the members will be either in the set or not. But in fuzzy theory, we say that the membership value represented by the sign mu, it will change between 0 and 1. It will not be either 0 or 1, but between 0 and 1. So for certain members of X belonging to set A, the membership value will be 1. For certain members of X not belonging to A, the value will be 0. But for many other members, they will be partly belonging to A, and the value of membership will be 0 to 1. The same example of age variable. From age 0 to 30, we can say the individual is young, but as soon as the individual crosses this value 20, on x-axis we put age. When it crosses 20, we see the membership of belonging to the set young, fuzzy set young, reduces. On y-axis, we put membership to the set. So after 20, membership to young reduces, and we cannot say young to an individual with age 36 or 37. At the same time, after age 20, the belonging to the set middle age starts. The membership to middle age starts, and it becomes 1 from age 32. From age 32 to 42, you find the individual to be a full member. The membership value is 1 of middle age. After 42, the membership to middle age starts decreasing, and membership to old starts increasing. And after 50, you see that after 60, all people who have age more than 60, they cannot be called middle-aged. So they're belonging to old age fuzzy set. The degree of belonging is 1. Here, we just created a linguistic variable to deal with uncertainty in language when we describe age using 3 words: young, middle-aged, and old. So young, middle-aged, and old are natural words, and at the same time, they are mapped to the numbers that machine need to work on. Machine now can understand that age 55 is slightly old and slightly middle-aged, and it can measure that degree of membership on the y-axis. So same member 55 can belong to old and middle-aged sets. Very simple but effective concept to capture vagueness in natural language. Let's study this membership function in a little more detail. We will interpret a membership function in terms of the universe of discourse. On x-axis, we will put the universe of discourse, all the numbers that this variable can take. Age cannot be 200 for humans. Age cannot be -5 for humans. So all possible values ordered on x-axis from minimum to maximum will be the universe of discourse for a membership function. The next term is the membership value. On y-axis, we will put the mu, membership value, which represents the degree of membership. Degree of membership is not equal to probability. This is very important. In fuzzy logic, degree of membership does not correspond to the probability of belongingness. Degree of membership comes from the uncertainty in language, not from the probabilistic formulas. Membership is not the likelihood, but the uncertainty. Again, back to the same membership function, the blue shaded areas, we can see that these numbers from 45 up to 60 in the shaded area, these numbers belong to both middle age and old set. Between 20 and 35, the shaded area, blue shaded area, these numbers 20, 21, 22, 23 up to 35, all these numbers belong to both young and middle age fuzzy sets. So using this universe of discourse on x-axis and membership value on y-axis, what we need is the shape of membership functions to describe linguistic variables. Each linguistic variable will be represented by a function shape. This shape is arbitrary. Every linguistic variable will take, depending on the context and meaning of that variable, it will take its own different kind of shape. Another example you can have a look on in the slides shared in the course shell in week 5 about the temperature. Here we use many membership functions to represent linguistic variable temperature that is expressed through many words, very low, low, medium, high, and very high. In case of crisp sets, we will face with the brittleness of the systems that depend on crisp sets. So one number above the threshold will be member of the next group and not member of the previous group anymore. But in case of fuzzy set, we allow the membership of one number to multiple sets using these linguistic variables. So your data will change its form. You will transform in case of, let's say, we have one variable for height for every person in this data set, Chris, Mark, John, Tom, David, and their height is 208, 205, 198, 188. And the membership to tall and short sets, if we define using crisp set theory, it will be 1, 1, 1, 1 for the people who have height more than 180, and everybody else will be 0, 0. And that would be unfair with David because his height is 179, just 1 centimeter below to belong to the next set. However, if we look at the fuzzy membership value, then we can assign the height to tall set or short set with a degree of membership value. So first two are surely tall, third and fourth are 0.98 and 0.82 tall. David is 0.78 tall, which is still better than considering David as short. The shape of crisp sets will be looking like this, a step function, but fuzzy sets will transit to the one concept to the other one in a smooth function. They can take multiple possible faces, shapes. For example, the value 2 is represented here using 4 different shapes of membership functions. Depending on the context of usage, depending on your application, you will choose appropriate function. A membership function can be triangular, trapezoidal, Gaussian, sigmoidal, or product of 2 sigmoidal functions. Here are some interesting properties of a membership function. In a given membership function, you will describe it using these concepts. So the core of membership function will be the area of the membership where all members within that area have membership as one, full membership. So this is the core of the membership function. From non-zero membership value, this point up to this point is going to be called as support of the membership function. The boundary is going to be all the values where the membership is below 1. So this area and this area are the boundary where the values are partially member of this fuzzy set. Core, support, and boundary are 3 things that you will use to discuss your membership functions. If a membership function has no member as having full membership to the set, you will say this function is subnormal. If there is at least one value in the universe of discourse on x-axis, there is at least one value that has full membership to the set, then that membership function is normal. Next, if you have just one peak in the membership function, then your membership function is termed as convex. If you have multiple peaks, so membership is increasing and then decreasing and then increasing again, so you have a non-convex function. You can combine 2 membership functions and calculate the intersection. The intersection of 2 convex fuzzy sets produce a convex fuzzy set. You can add 2 membership functions, so adding A and B results in a convex membership function A plus B. Similarly, adding A and B here will result in this function A plus B. Corresponding to all the Boolean operators that we use in crisp set theory, we have fuzzy operators, also called Zadeh operators. So for intersection in Boolean logic or in propositional logic, we used AND operator. In here, we will use min operator. OR operator will be replaced by max. NOT operator will be replaced by complement, 1 minus fuzzy membership function. Diff between A and B will be represented by min between A and B, and diff between B and A will be represented by min between B and A. You can look at this example to see how these operators are working on a data set. So we have X with members 5, 10, 15, and 20. The degree of membership for a variable linguistic variable A, 5 is 0.2, 10 the degree of membership is 0.4, for 15 the degree of membership is 0.4, for 20 degree of membership is 0.4. Similarly, we create another linguistic variable B. Notice the tilde sign that we use to denote linguistic variables. B tilde represents another linguistic variable where 5 has membership value as 0.4, 10 has membership value as 0.1, and so on. So if we want to do intersection, A and B, A tilde and B, we will apply intersection operator, and intersection will do this. Whenever the minimum value of membership between A and B for member 5 will be the intersection. So for 0.2 and 0.4, the minimum is 0.2. So in the resulting intersection function, we will say 5 has the membership as 0.2. For 10, it will be 0.1. For 15, it will be 0.1. For 20, it will be 0.2. If you want to take union of both the sets, then you will take max of the membership value. So from 0.2 and 0.4, the max is 0.4. So the value 5 will be associated with A union B with the degree 0.4. 10 will be 0.4 because it is more than 0.1. 15 will be 0.4 because it is the max of 0.4 and 0.1 is 0.4. Value 20, the degree of membership will be 0.4 because the max of 0.2 and 0.4 is 0.4. So you now understand, when you take intersection, you take minimum of the membership values. When you take union of two fuzzy variables, you take maximum of the membership value. Complement, in case of complement, you will subtract the membership value from 1. So A complement will be 1 minus 0.2. The membership value for 5 will be 0.8. And so on. B complement and A intersection B complement you can do after you review the materials. If you have any question, please share on the Teams in the channel week 5 fuzzy set theory and expert systems. Once you have defined all these linguistic variables for your problem, how you build and actually construct an fuzzy expert system. It will take a crisp input. Let's say you are building a controller, fuzzy controller for air conditioning. In that case, your system will take a crisp input, a number, and then you will fuzzify with the help of linguistic variable A, B, C, D, whatever is the complexity of your system, how many variables you define. Using those, you will go through a fuzzification phase. The fuzzification component will take the crisp input, numeric input, and transform it using the linguistic variables into words. Those words you will use to invoke the fuzzy rules in your knowledge base. Instead of having the propositional logic based rules that we did in the last week, for example, A leads to X, B or C leads to Y, D and A leads to Y. These rules will have the same formation, but A and X will be the human language words coming out of linguistic variables. And based on those words, word-based rules, we will input to the fuzzy inference engine. So the inference engine you worked with in last week, all the rules will be taking inputs as fuzzy variables, not the regular variables. Fuzzy inference engine will compute the result, and then you will combine the outputs. From these three rules, let's say, you will combine whatever was the input. Based on that, you fuzzified and did some inference, and now you need to compose the output and defuzzify it and make a crisp output, the numeric output. I will explain this with an example. Let's say we visit a restaurant, and over there you need to follow these rules while you are giving a tip. Rule number 1, if the food is bad or the service is poor, then the tip will be low. If the service is acceptable, then the tip will be medium. If the food is great or the service is amazing, then the tip will be high. Now, we don't see any numbers in these rules. These rules are expressed in natural language. Let's say you are given these values. Food quality was 6.5 and service was 9.8. How much tip you will give? So based on these rules, we need to calculate a number that satisfies these rules but processes 6.5 and 9.8. Quite a challenging task if we use crisp set theory in the techniques that we were using till now. Let's say we create linguistic variables for food quality with three values: bad, decent, and great. On the x-axis, we put the universe of discourse. For the food quality, it can be 0 up to 10, and the membership value will be on y-axis. So the bad word will be mapped with this function, the blue line. So as long as food quality is below 5 food quality, we will say it is bad as much as this number on the y-axis corresponding to the blue line. Above 5, if the food quality is above 5, we cannot say it is bad. The membership to the bad set will be 0 for all values above 5. Similarly, decent food quality, the membership will value increase after 1, 2, 3, 4, and if the membership is the value for decent word function is 5, food quality is 5, then the membership value will be 1 for decent function. Food quality great will be represented by this red membership function. If the food quality is less than 5, then the membership to grade is 0. Above 5, the membership to grade is increasing, and for value 10 for food quality, the membership to grade function is 1. You can trace the interpretation of all other variables, service quality, and tip in the corresponding plots. Next, let's process the crisp inputs 6.5. Food quality 6.5. Is it bad? Is it decent or great? So we have 6.5 here. We need to look at the membership value. For great, it will be around 2.2. And for decent, the membership value for decent function will be around 6.5. So the 6.5 food quality will be represented by three fuzzy functions: bad, decent, and great, and we will get their corresponding membership values. Similarly, for service quality 9.8, we'll get the membership value for poor, acceptable, and amazing functions. And based on these two, we will calculate the tip amount. And those calculations will involve fuzzy inference rules. If food is bad or service is poor, then tip is low. How low is defined, it is shown here using the blue line. Let's see how rule number 1 is executed in the fuzzy inference engine. Food is bad or service is poor, tip is low. OR function will be the max function. If you remember, in the previous slides, we looked at OR function. The corresponding function is max for the fuzzy sets. So we will take max of food is bad is 0, service is poor is 0, and tip is low. Whatever is the max, we will take that, and the output of this OR leads to tip is low. So this arrow sign will be represented by min. So min of max of these two variables and tip low will be the output of rule number 1. For rule number 2, this will be the output. When service is acceptable, which is 0.04, the min of acceptable service and tip medium function will be rule number 2's output, which we can see here, this shaded area. Rule number 3, if the food is great or service is amazing, then tip is high, will be represented in the fuzzy inference engine using food great value 0.4, service amazing value 0.96, and we will take max of these two. The output of that max, we will take min with tip high. So the output of first for this function will be rule number 3 will generate this shaded area. When we combine in composition, we combine all three aggregated outputs from rule number 1, 2, and 3. So this yellow area from all three rules will come out of the fuzzy inference engine. We'll find the midpoint or the centroid of this shaded area. And this midpoint is your tip amount. So fuzzy inference engine will recommend that you give 19.8, around 19.8. So in fuzzy expert systems, we allow complicated but intuitive behavior. And with minimal computational overhead, we don't involve complex matrix algebra here. We just put a little more interpretation to the words that connect numbers with the words. We can achieve a very intuitive and insightful interaction between humans and expert systems. You can adjust system performance by providing better membership functions, and the systems will be stable because small changes in the inputs will result in small changes in the outputs. So there will not be any issue with the small changes in the input cannot cause a drastic change in the output. For the implementation part, I would encourage you to have a look on skfuzzy library. I will share the solution of this tipping restaurant problem. You can have a look in the next sitting. We will go through the solution with the help of some other examples where you can get more hands-on experience with building fuzzy expert systems. Different membership functions that I discussed in the slides, you can find in this library in membership module. For more details, I would encourage you to study these papers. And now I would like to discuss more about this topic with your questions and comments.